In this video, we'll continue our discussion of curvature by using some theory to get to an alternative formula. So I'm going to drag you through this theory. So let's start with just a position function given there. Just a general position function. And it's going to be the typical case where we take our derivative and we get velocity. I take the derivative of velocity and I get acceleration. Normal stuff there. And we're going to assume that it's not a zero velocity or zero acceleration. And then we're going to begin our whole discussion working on this idea. So remember our tangent unit vector, you guys may remember it better like this, okay? It's instead of velocity, it was r prime over t over the magnitude of r prime over t. That was our tangent unit vector. But they just used velocity here. Okay, so what they did there is they multiplied both sides by the magnitude, so we are here. Okay. We can now use this definition to go, okay, if I take acceleration, acceleration is the derivative of velocity. So what they're doing here is they're going to take the definition that we just came up with here, and they are going to take its derivative to get acceleration. So we're going to start building this formula towards acceleration. All right, acceleration, we take our formula, our derivative. This is just a chain rule. So notice that this was derivative of that function times the second function. And then I left the second function alone, and then we took the derivative of the t, the second function. That's just a product rule there. All right, so notice here, we just came up with a term here, or an expression for acceleration. So I know that acceleration is equal to, I'm going to erase everything else. Everything else is we're not going to use for a moment. Okay, so we have that acceleration is equal to that. So now what they're going to do is we're going to work on a cross product here. Velocity cross acceleration. So notice that they took velocity, which was up here, and then they replaced it with what it is. And then also they took that definition and put it there because that was acceleration. Okay, properties of cross products is they distribute. So notice that this just cross distributed with that and with that to give me, okay, there's the first distribution, there's the second distribution. Okay, let's take a look at this term first. I want you to notice that two of these terms are big T of t. The other terms that I did not highlight there in green, the light green, those are actually, like, let me show you what I'm talking about. This one, that is a scalar. This is also a scalar. So we have the form, and this is what they're talking about here, some scalar times t and some scalar times t there. So those are scalars, so when I cross them, well, if they are scalars of each other, they're parallel. So when I cross them, they run in the same direction. So that means this whole term here is 0. All right, to simplify the second term, recall that the vector of constant length has the property that u and du dt are orthogonal. I'll prove this here in a moment because we're going to use it in another video. So I'll verify this a little later. Okay, so because t is a unit vector, is a constant length, and t and dt are orthogonal. Furthermore, the scalar multiples of t and dt are also orthogonal. Okay, so what they're going to do now is we have this term here. We're going to take that term and we're going to find its magnitude. So that's what we got here. If we take its magnitude, this is a definition that we came up with in a previous video. I know it's this vector, the magnitudes of each one separately, and then the magnitude of the next one. So this is like magnitude of the first cross, this is magnitude of this one, and then sine of the angle between. But we can, magnitude of a magnitude is just the magnitude of itself because it's not going to do anything, just a single term. So this thing comes out, giving us that square there. And then we just kind of rewrite everything else. This is dt, right? And then here's the trick here. Sine of, and then this is where this stuff comes in. This felt like out of nowhere almost, like, okay, cool, great. Now where do we use that? Well, that's used right here. if they're orthogonal, that means that theta is pi over 2, or 90 degrees, which means that this is equal to sine of, let's just do it over here, sine of pi over 2 is 0. Or, sorry, not 0, 1. Whew. Okay, so that means that's where that went. This is just a times 1. They rewrote this term, dt, they just wrote it like that. So all they did is rewrite everything. Oh, I lied to you guys. dt is not that. That's where that went. This t and that t, they're different, right? One is t and one is the derivative of t with respect to t. Right? If I continue with that definition, well, t, so the t that's highlighted now there, is a unit vector. So the magnitude of t is 1, because it's a unit vector. It's the unit tangent vector. So that's why that's gone as well, leaving us with that last thing. So we know the cross product of v cross a is equal to that. I'm going to write that right here. That's what we just came up with. This term right there. Okay, now we have this definition that curvature is equal to that. We can replace, by solving for dt, we have that, so we can replace that with that last step, leaving us with curvature of the magnitude of velocity to the third. So doing all those replacements, right, replacing this in there, we have this equation. I'll highlight the important parts of the equation. The other stuff just shows how we got there. All right, so solving for curvature, this is our new formula. This is only great typically when these are polynomials. Outside of that, think about it, you take a derivative of derivative. If I got to get to acceleration given an rt, and I got to get to that, that's 2 derivatives. If it's a chain rule, with a power rule, with a product rule, like all that can get really nasty. But if I do polynomials with each derivative get simpler. I'm going to give you another definition here. This is typically what books give. They'll do magnitude of r prime of t crossed with r double prime, because that's acceleration. And then they'll do the magnitude of r prime of t to the third. That's what you'll typically see in textbooks. All right, so this is our new formula. We're going to do an example, I think 2 of them, using this. Okay, find the curvature of the parabola. There's my function from all real numbers of t. Okay, so using my formula above, I need the r prime and r double prime, so let's go ahead and do that. So r prime, this is what's nice. Those are both polynomials, because r prime is 1, and then negative 10t. And then I have r double prime. I got 0, negative 10. All right. Now this says we're going to need the cross product of, the magnitude. Well, we will need the cross product as well. The magnitude of r prime, okay, that's going to be the square root of 1 plus 100t squared. Doesn't simplify. Do not separate square roots across pluses. All right, so we have to now take our cross product of r dot t with r double prime of t, and then we're going to have to find its magnitude. Actually, let's use, no, we don't know the angle between. Let's not do that. All right, so we have to do this cross product. So let's list this out. Okay, now one thing you may think about is that there is not a third component. Cross products only work in 3 space. So what we're going to do is just put a 0 and a 0 there for our z component, since it lives in the xy plane. Now, it makes sense to do a cross product. 1, negative 10t, 0, 0, negative 10, 0. All right, so we have the first one covering up your i's, 10t, negative 10, 0, 0, I, minus, cover up the j, I got 1, 0, 0, 0, j, plus, cover up the k, I got 1, negative 10t, 1, negative 10, and that is our k. Everything goes to 0 except for the k one. That's going to get me a, oh, there should be a 0 there. Right, okay, negative 10k. But they also want the cross product, the magnitude of that, of the cross product. So that is that. And I'm going to square it, take it, I get 10. Okay, so curvature is equal to, the cross product goes on top, and then the magnitude goes on the bottom, but it's to the third power. So all that to the third. You could simplify this. I guess we could do that. 10. We could take 1 out of that. Sorry for my bad line there. There we go. Perfect line. All right, 10. And then I could do this. 1 plus 100 t squared times the square root. Square roots don't fix itself. There we go. Sorry, I don't know why my hand's so shaky today. There we go. And I got 1 plus 100 t squared. I could do that. I would be happy with the definition before. So anyway, there's a new definition. It's really nice when you have polynomials. But like if you were to start throwing, cosine of t squared minus 4, and you start doing that, sorry about that, times 4 minus 4, then like when you take a derivative, the function becomes more complicated. So if I had to go all the way up to a double derivative, the function itself is going to get way complicated. Okay, let's do another one. So now we have a helix, so like a DNA strand, right? Just a single path. They give me that, and they want us to find the curvature. So I'm going to write down that formula. Curvature is equal to the magnitude of r prime t crossed with r double prime of t over the magnitude of r prime of t to the third. So I need to find each case now. So r prime of t will be negative 13 sine t. Then we got 3 cosine t, and then we have pi. So there is my r prime. Let's do r prime of t magnitude. Okay, so we're going to get the square root of, 13 squared is 169 sine squared t. Right, and then I square the next one. I got 9 cosine squared t. And then I have pi, and those should all be pluses in between. Sorry, my brain was thinking about something else. Pi squared. There we go. I was thinking about these numbers being a 3 and a 13. I'm debating if that's a helix. It'd be like an oblong helix, I feel like. So, okay, so there's that. It's not pretty. I can't manipulate that in any way. Okay, r prime of t is going to be negative 13 cosine t, and then negative 3 sine t, and then 0. All right, I want to cross those. All right, so I got I, J, K, and then we got negative 13 sine t, got 3 cosine t, pi, negative 13 cosine t, minus 3 sine t, 0. Okay, so cover up the I column. I'm going to do this a little to keep the video kind of short. Here's that. We're going to get a positive 3 pi sine t I. All right, I do the next one. Cover that one up. I got a minus, and then it's going to be 13 pi cosine t j. Cool. All right, and then one last one. I cover my third column up, and I'm going to get plus 13 times 3 is 39. 39 sine squared t plus 39 cosine squared t k. So what this is going to get us is 3 pi, let's throw these in angle brackets, 3 pi sine t, comma, negative 13 pi cosine t. And then this last thing, if I factor out that 39, then that goes to 1, and I get that. Okay, so now I also have to take the magnitude of this thing. All right, magnitude. Sorry about that. Okay, so if I square that, I got 9 pi squared sine squared t plus 169 pi squared cosine squared t plus, and I'm going to be lazy, I don't have a calculator on me, 39 squared. All right, that won't simplify, so that's okay. Do I have r prime? I did find the magnitude of the other one. So this is going to be curvature is, okay, and I'm going to cheat here. I'll just duplicate this. That goes on top. And then this thing here, r prime, goes on bottom. And I'm going to cube that. I would leave that there. That looks like a great answer to me. It's really nasty, but that's okay. If I plug in any t I want, I can have curvature. This is why maybe that other formula would be better here than this formula, because that got really nasty. I typically only use this formula for curvature if they are polynomials, because the derivatives are nice and pretty and everything gets simpler as we go along, rather than any kind of transcendental function, you know, cosine, sines, anything like that. They're going to get pretty crazy. So I typically stick with the first curvature if it's nasty, and then if they're nice polynomials, this definition is great.